Welcome back. Today we're going to look at data variables and memory. So when a variable is declared in memory, what you're actually doing is reserving place in the RAM, the random access memory of your machine. The number of bytes are actually dependent on the type of variable, and if you look in the chart in your book, or you can go online and find the variable sizes in Microsoft documentation, you'll see that different types of variables have different amounts of memory and a resulting difference in precision. So you'll notice here, for example, an int has 4 bytes of memory, and it can represent a number from minus this really large number to plus this really large number. A char, on the other hand, only has 1 byte of memory, and a byte of memory is represented with 8 bits. So each byte is 8 bits. And so with 1 byte of memory, we can represent 256 numbers, or in the case of a char, it can represent from minus 128 to positive 127. An unsigned char can represent from 0 to 255. So why is it that we have this difference when they're really the same amount of memory? Well, one of the bytes, or one of the bits in a signed number, is used to represent whether the number is positive or negative. And so that means that the magnitude of an unsigned number, while it can be up to 256 different numbers, with an assigned one, it's half that. So it ends up being from minus 128 to 127. And it's a little more complicated than just the bit is representing plus or minus. There's a whole scheme involved that if you were doing assembly language or machine code, you would really need to know. But for our purposes, we can look at the chart and see that a signed number has about half the magnitude and can represent negative numbers, whereas the unsigned number can represent about twice the magnitude but can't represent negative numbers. And if you were to look, for example, at a double, 8 bytes, and it can represent up to 10 digits of precision, and it can represent positive and negative numbers. Maybe a better example is in the integers. You can see a long int has 4 bytes. It can represent from minus, let's see, about 2 billion, I guess, to positive 2 billion or so. So this type of variable you declare determines how much memory it takes, which, normally the more memory you take, the more intensive use of resources you have, to the amount of precision. So a higher number of bytes uses up more memory, however, it gives you more precision. And precision in integer numbers kind of makes sense. It's just, larger numbers. With floating point numbers and doubles, what it results in is the number of digits of precision that you can represent with that number. Notice that we don't have an infinite number of digits of precision with floating point and doubles. You have a finite amount of precision you can represent with a number in a computer. So one way that we can look at this is C++ provides a size of operator, which returns a number of bytes that whatever it's used with has. So if you use it with a variable name, you just can put size of and then the variable name. You don't need parentheses. You don't have to call it like a function. And what it will return is how many bytes that variable takes up. And then if you use size of and you put a data type in parentheses, it will show you how much memory that data type takes up. So here's a program which illustrates that, and we are declaring a char, a double, a float, an int, and a long, and we can see the size of operator being used here. And if we run that, and this is one of the sample programs for the book, we can see that our char takes 1 byte, our double takes 8 bytes, our float takes 4, and takes 4, long takes 4. And Another way you could do this is you could say something like that. And you see that it provides the same information. So you can either call size of with a variable or with a type. And if we look back at our chart, we can see when we ran the program, the char is indeed 1, the double is indeed 8, the float is indeed 4, the int is 4, and then the long is also 4. So the way the computer works with variables is it reserves actual memory locations in the variables. However, the program doesn't actually know where it is in memory until the operating system actually runs the program. So when you compile your program, it's actually kind of putting placeholders in for your variable names. And then when you run, then the variable names will actually show up, or the variable names are associated with the actual position in memory. And this kind of works through something called the stack. So where variables are placed on the stack at runtime, and it's a region in memory reserved for programs to store their variables. And when the operating system runs your program, it then allocates space on the stack for you and puts your variables will then start being placed on the stack. So it just depends where your variables end up in actuality during runtime. Just depends on when the program gets run and when the operating system allocates or gives you the stack. The way the stack works also is the variable is placed on the far end of the stack. And this kind of illustrates what this looks like. So here we have some variables being declared. You have X is the first one, Y is the next, I, J, K, and then R is the last. And so when the instruction pointer gets to this first one, this variable X is pushed onto the stack and it's over at the far end. And as you go forward, they each get placed from the far end to the near end. What this looks like in a diagram is this. Here we have our stack, and you can think of the far end as being at the bottom, and you just keep stacking your variables on top of each other until you go up to the low end. So the address for X will be a larger number than the address for R. Computer memory is also addressed using hexadecimal notation. All hexadecimal notation is a way of representing, it's a more efficient way of representing binary numbers, and it's really to make it a little bit more readable, because in actuality, the addresses in the computer are stored as binary numbers. And so you'll see this notation where it's 0066FDF0, and you wonder what these letters are for. So to understand this notation, let's take a look at different types of numbering systems. And so we have decimal, binary, octal, and hex, which are often used in computer programming. And decimal is just the normal decimal numbers, and we have them represented from 0 to 32 here. And the rule for binary is that you can only use a 1 or a 0. So right out the gate, we can represent zeros all across the board easily. 1 is easy to do. But then with binary, when you get to 2, well, we don't have a 2. We only have a 1 and 0. So what we do is we do the same thing as is done when in the decimal system, you go from 9 to 10. You don't have a 10 character. So what you do is you put a 1 over on the left side and a 0, and you start back from 0 again and just keep proceeding on. Well, with binary, you apply the same type of algorithm. We have a 1, we don't have a 2, so we put a 1 over in the second position here, and then we start with 0, and then we repeat. Well, then we can put a 1 for 3, and then we run out of, we can't go beyond 1, so we put a 0, and we would add 1 here. But again, we don't have a 2, so it becomes 1 0 0. And you can see this is how binary moves forward. With octal, we can use any number less than 8 as, and octal means 8. We can use any number less than 8 in order to represent the number. So from 0 to 7, it progresses the same as the decimal number system, but then we don't have an 8, so we can't represent 8 the way we can in decimal. So we have to use a 1 0 and start back with 0 in the ones position, and then you proceed on. When you get to 17, you don't have a character for 8 again. So then you go to 2 0. So 2 0 in octal is equal to 16 in decimal. And the way you can get there is realize octal is base 8. So if we multiply the number on the left by 8, 2 times 8 is equal to 16. Now let's go to hexadecimal. With hex, you can represent with one character anything less than 16 characters, or 16, the number 16. So with hex, we are permitted to represent with one character the numbers from 0 to 15. Well, here's the problem. From 0 to 9, it looks just like decimal, but then we get to 10. And the rule is with hexadecimal, which hexadecimal means 6 and 10, which is 16. You're not allowed to go to 1 0 until you get up to 16. So how do we represent 10 when we are not allowed to use a 1 0 in hexadecimal? We start using the alphabet. So we get A, B, C, D. So A is 10 in hexadecimal, B is 11 in hexadecimal, C is 12, and so on, all the way up to F, which is 15 in hexadecimal. Now, once we get to 16, we're allowed to use a 1 0 to represent hex. So 16 in base 10, or the decimal system, is equal to 10 in hexadecimal. It's 1 0. And you really shouldn't say 10, really. It's really 1 0. 10 in, so 1 0 in a hexadecimal is 16. 10 in decimal is equal to A in hexadecimal. And then if you look as it progresses on, you can see from our hex, 17 is 1 1. And again, the way you figure out what is this number, just multiply the number in this position by the base type. And so hexadecimal's base is 16. So 1 times 16 plus 1 is equal to 17. 1 times 16 plus 2 is 18, and so on. And notice again, when we get to 19, we can't just go, it's not 20, that would be 32. It's 1A, 1B, 1C, all the way up to 20, and 20 hexadecimal, 2 times 16 is 32, so that's 32. So you don't really need to know that in great detail for C++ programming. If you were to go on to machine code or assembly language, you would need to know that quite intently. But it's just to explain why our memory addresses are hexadecimal numbers. So this memory is 66FD8, and so this is the hexadecimal number. And you're not going to need to decode these memory addresses. We're providing it here so that you understand that these are just numbers and they're positioned in memory. And so here we have our variables, and you can see that they're, as we declare them, floats take 4 bytes of memory, and so they're at this position. And when we go to Y, since we start at the far end of the stack, we're actually going backwards in memory. So 4 bytes before 66FDF4 is 66FDF0. So if we take a 4-byte number and subtract 4 bytes off it, the start of Y is at that location. The start of I, again, it's 4 bytes for an int as well. So F0 minus 4, well, we have to take F, it goes to E, and then A, B, C, 0, A, B, or so if we subtract that, so if we were to go C, D, E, F, C, D, E, F, that would be 3 letters, and then fourth one would be, we would move up the next position, which would give you F0. So you can look at the previous chart and kind of work through these. Just realize these are being placed backwards in memory on the stack. And here's another representation. And you can see in this one, they've assigned values into the locations. So what that would look like is this. You have these places in memory. And as we do assignment operations, 1 is going into X, 2 is going into Y. And so remember, we want to read this not as an equals, but as assigned into. So when we say 1 is assigned into X, that means that 1 is being placed into that memory location. So the way you should think of your variables is the identifier is a representation of a place in memory, and we're placing a number in that place in memory. Same thing here. 3 is going to I, 4 is going into J, 5 is going into I guess that should have been Q. So 5 is going into Q. And notice because Q is a double, we're representing the doubles and the floats with their decimal points. In actuality, these are all being placed in as 1s and 0s. And then 6 is going into R. And also what we're doing here is we're representing the level of precision with the decimal points and the number of zeros behind it. And with doubles, which have 8 bytes of memory, they can have twice the precision of the ones of the floats. So how many bytes does an int take up in memory? Pause, think of the answer, look it up. There's a table for you to look it up, and then hit continue. So there's actually Microsoft has a website, and if you search for MSDN size of types, you'll find that there's a data type ranges article for C++ language. And you would imagine that, you have this, you can look up this kind of thing online at any time. And in our case, we want an int. So here's an int, and we see it takes 4 bytes, and there's the range. And you can see this has a full list of all the different types. So that's where you can find your documentation, and the answer is 4. So this is unfortunate. It's answer 3, which is 4 bytes. How many bytes does a double take up in memory? Again, pause, think of the answer, and then hit continue. If you look at the chart again, we're looking at a double. So we'll scroll down till we find a double. There's a double, 8 bytes of memory. So the answer is this one. Write the code that returns the size of a variable called myvar. So pause, maybe write down the answer, and then hit continue. So let's see. We saw the size of operator. And so maybe we would see out. Let me see if I can get a better pointer. And so it might look something like this. So that would size of operator will give you the size of the variable. And let's see. So the next thing we want to look at is how do we get the address of a variable when we're running our program. So each variable has a data type, an address. To access the address of an operator, we can use the ampersand operator. And what that does is it returns the actual address of the variable itself. And so if we were to do something like this, that would output the hexadecimal address of my var to the screen. So given a variable called my var, write the code that will return the address of its location in memory. I kind of gave it to you. So pause, think about the answer, and then hit continue. So yes, this is what you would write to get the address of my var. So if you didn't have that, you would get the value in my var. If you put the ampersand operator, you get the address of your variable. So our variables therefore have these 5 properties. They have a data type, which is what type of data that variable holds. The value, which is what's actually in that location memory. The name, which is the identifier you as a programmer have given it. A memory address, which is where that variable is in memory, and then how much memory which is reserved for the variable, which is implied by the data type. So variables, how do we declare a variable? And let's say we want to declare a variable num. Well, you've already done this a number of times, but now you should be able to see this in a little bit more detail. So when you say double number 1, what you're doing is you should now see that you're reserving a place in memory, and you're providing an identifier for you to refer to a place in memory. So what happens when we declare that variable? Well, here we have our declaration statement. And what's happening is when you say double number 1, you're providing a place location memory which is going to have an address that will be allocated at runtime. And you're using this identifier to refer to it while you're writing your program. If next you then do an assignment operation, what you're doing is you're setting a value into this location memory, which is represented by number 1. So 6.0 is going to go into 66FDF4. So that's why we want to read this equal sign as assigned into. We're assigning 6 into the location in memory represented by the variable name number 1. So that concludes what we want to talk about today. Thank you very much.